Hi, and welcome to this video demo about finding small features using Polygonica, and in particular using the thickness, gap thickness and protrusion meshes. My name's Richard Baxter. I'm Head of Sales and Marketing at MachineWorks, which is the company that develops Polygonica. So first to say, we're on LinkedIn. We're pushing content out on the LinkedIn channel. So if you're interested, feel free to follow the MachineWorks Limited page and/or either of the Polygonica or MachineWorks SDK software development kit pages. It's a great way to stay in touch, great way to update. And similarly, if you're interested in connecting with me, I'd be very, very happy to increase my connections as well. So within Polygonica, there's a data type called a PT analysis mesh, and that's the resulting data type from one of these types of analyses. And what that is a mesh that's created from evenly spaced sample points across the surface of the part. So in order to get a good analysis, Polygonica generates evenly spaced sample points. And then in the analysis mesh, each of those sample points is a vertex in that analysis mesh, and each vertex contains distance information. So currently there's 4 types. There's the original analysis mesh, which is the nearest distance to another mesh. So that's like the heat map analysis you'll typically see in metrology applications. So for example, if you have a laser scanned result and you want to compare it to the original design part, then you do a heat map to see how it's changed. And you might also use that for automated QA kind of thing. So you've got a reference part that's been generated by one laser scan, and then you measure points on parts on the production line and compare with that. So that's a sort of fairly typical thing. For the thickness mesh was developed specifically for the additive industry, and it's a very quick visual display of where there are thick or thin regions in the part in order to figure out, is this part printable? And that's been in Polygonica for some time. But we've now added 2 more, gap thickness mesh and protrusion mesh. So gap thickness mesh is a similar concept to thickness mesh, but instead of firing rays into the part to find the thickness, it's firing rays out from the part to see if there are any gaps. So if a ray is fired out and it hits another bit of the part, then it measures that region and reports this is the thickness of this gap. So that's really good for finding holes and pockets and things like that, particularly ones where the insides of the holes may not be even, in which case then it's difficult for surface detection and feature analysis to say that this is properly a hole feature, because it looks more complex than a hole. So that's part of the reason why we added it. And then protrusion mesh, well, I'll explain that in more detail later, but basically if a wall is too thin, whether that's printable or not actually depends on the height of the wall. So a thick wall might be printable to a higher height than a thin wall. And so protrusion mesh is designed for finding the height, if you like, of thin regions. So what you get back in the analysis mesh is a mesh that you can display, but also a bunch of coordinates in space with distance values, which you can extract and put into your own graphics and render, or put into reports for auditing or whatever. Or you can say these things are outside threshold values and generate your own images. But Polygonica's inbuilt graphics engine can also draw them for you as a heat map, which is what you'll see later. But most of our customers are using their own graphics engine, so generally they'll take this information out and render it in their graphics. A couple of points about this sample-based method. So first of all, it's sample-based, so it's only really as accurate as the distance between the samples. If you have a very large distance between the samples, you're likely to miss information. So Polygonica offers control over the maximum edge length, or the maximum distance between sample points. As you decrease that, you get a more accurate analysis, but also it takes more memory and more processing time. So for automation, for example, if you're doing an automated check, you might well want to increase that, and it might take longer to run, but it doesn't matter because it's being done offline. There's not a user watching it, and you generate a report that's studied afterwards. If you're doing interactive viewing, you're probably going to want a smaller, or you're probably going to want to have a larger gap between the sample points. And Polygonica will generate that for you. It'll pick a reasonable spread, as a default, and I've used it on a wide range of different models, and it seems to do that pretty well. The other point being that if you're doing this, you do need to have an even spread of sample points across the surface. So, for example, if you look at this is zoomed in part of a large engine model I'm going to show you in a bit, and you can see that there are large triangles here and triangles with very long edges. So on those sort of larger surface areas, some of which are curved, and there's internal geometry here, which is important, there would be no sample points. If you just use the vertices in the existing mesh, you would miss tons of information. So it's really, really important that you do create an even sample across the surface. So just talking about protrusion mesh specifically, I think the easiest way to conceptualize it or think about it is the height of a thin wall. So if the wall is 5 thick, then it can be this height. If the wall is 2 thick, then it can only be that height. But we've used the term protrusion because this is orientation independent. I mean, all we're doing is measuring the distance of a point in the thin region from the nearest thick region across the surface. So that's roughly what's happening. There's more to it under the hood, but that's a rough way of thinking about it. And the way it works is it finds protrusion values for regions thinner than a given thickness. So, for example, on this part, let's say I said that a region must be, or a thin region is 2 or less. So the colouring shows in grey regions are thicker than 2. So the base is thicker than 2, except at the edges. And then green and red are both thin regions, so those regions are smaller than 2. But green is okay because the height or the protrusion distance is less than the tolerance I've specified, whereas red is further away than that protrusion. So in theory, that's not printable. Obviously, I've just picked some random values here to make a pretty picture. I mean, this isn't based on any particular real material. I just wanted to illustrate the point here. But yeah, in theory, those red regions wouldn't be printable, and the green regions would be, but they're all under that thickness threshold of 2. We're doing more development in this area. That development will be prioritised based on customer feedback. So we're working with customers who are interested in this type of analysis, and to be honest, I think a lot of people in additive are interested in this kind of analysis, and it's not straightforward to do it automatically, and that's really what we're working for. So Polygonica already has surface detection and feature detection, and we're looking to add these techniques to that arsenal of ways of analysing the mesh to try to get better automation results. It's very likely refinements and optimizations will be needed to these techniques for printability analysis, and potentially if people in other industries start using them. And the work on that will be prioritized based on customer feedback. I mean, another area, for example, that we're looking at is defeaturing of really complex models for CAE. So when you're doing a CAE analysis of a model, you don't want long, thin features in the model, but they can be very difficult to remove. They're difficult to identify automatically, so they might well need some customer involvement. But rather than have the customer picking each individual triangle in the mesh, we're thinking of using these kinds of techniques to find the thin regions, identify them, select them, and then allow the customer or allow the end user to remove them in one go, and defeature them like that. So we think there's quite a lot of potential in these techniques, but we'll post more videos as we move forward with this. That's our website. There's an about page or a contact page at the top. So if you do want to contact us to ask us any questions about this, please do throw that way, or find me on LinkedIn and connect with me, and you can ask me questions that way. Okay, so onto the demo. So firstly, this demonstration GUI, Polygonica demo, we call it, is just an internal tool we use for demonstrations and sales. It's not something you can buy, it's not something we give to customers, it's not something we give out for evaluations. It literally is just a demo tool, and it's built and maintained by the sales and marketing department. Okay, just a couple of things about the interface. So there's a few properties here, like for example the number of polygons in the mesh, in this case 71,000. Some traffic lights here saying, telling you about mesh errors, so interesting to keep an eye on. And let's go on. So this colouring here, the red parts are telling me that this is self-intersecting, as is the red bit there. Now the Polygonica, the analysis mesh will work with non-watertight, self-intersecting, non-manifold meshes. But since we're in Polygonica and it's easy enough to heal it, we might as well heal it. So in this case, I'm just going to click remove self-intersections, and that's done. I'll go back to the additive tab, and I'm going to start off showing wall thickness. So there we go, we can see the wall thickness in this. So anything in red is below this thickness threshold here of 1.04. So if you look at the dimensions of the part, it's 104 by 90 by 30. So we're looking at about, I guess, probably a millimetre there. Is that right? Yeah, probably about a millimetre. And then I can dynamically update this. So I've changed it to 0.4. If I drag it and make it thicker, you can see it actually updates, and whoops, a bit too much. So we're not recalculating the actual thicknesses here. All we're doing is changing the graphical display. And if I double click on one of these, it's going to tell me how thick it is down here. So 0.96, and let's just try another one. 0.7. Okay, you have to be careful. Yeah, they're not. I was going to say they're probably all uniform thickness, but you can see they aren't. 0.7 there. So if I select, yeah, let's see. If I just select about 2, that will probably get most of them, I think. Okay, maybe not. 2.5. And that's most of it. So you can see, and if I zoom out, that's done it on the whole part as well. So it's a really quick way of visualizing how thick something is in a part. And similarly, we've got the gap thickness mesh, which does the opposite. So it's now looking at, for example, how far apart are points on these two faces here. So if I can double click and it tells me that one's 0.5 and that one's 0.5, and my threshold here is 1. So let's just see what happens if I change that down to 0.4. And you can see, well, at the top here, they're within 0.4, but down the bottom, they're further apart. Let me just zoom out, and one of these big ones, double click, it's 3.2, 3.3. So if I put 3, let's say 3, it's probably going to get most of the mesh, but it hasn't got these, if you like, the centers of the circles, but it's found everything else as being below. And then you can see also on the sides here, these are bigger, whereas these bits are smaller. So just a very quick visual check, but also you can extract those values and put them in a report if you want to. So here's a more kind of maybe a more interesting part. This is some big engine, and you can see there's lots of tiny holes. But how would we know that? How do we know how big those holes actually are? So if I click gap thickness mesh, so Polygonica has created a sort of threshold value of 20, just automatically figure that out. And if you look at the dimensions, so this is, I guess, millimeters. The parts in that's 2 meters by 1.5 meters, maybe something like that. So it's a big object, and these things are 20 millimeter holes or 2 centimeter holes. I'm guessing maybe, and you can see that's most of them. But if I, for example, click on these, then the thickness in there is 16, whereas what's that one's 13, that one's 10. So let me just kind of change these down, 15, and we've got rid of that. Those holes, but we're still highlighting all those others. Let me change it down to 10, and most of them have gone because that one was just above 10. So let's make it 11, and then we've got these little holes here back. So yeah, a nice quick visual check, but also a way of automating finding holes and pockets in a large part. So I'm going to look at protrusion mesh now, which is a little bit more complex. But first of all, on this part, let's look at the wall thickness. So actually, before I do that, I'll just point out that if I look in transparency, this part's got lots of internals as well. So when you're looking at things like thickness, then it's going to find thin regions. It's going to find thin regions because it's going to, in some areas, because it's going to measure against some of the internal geometry potentially. Certainly with gap thickness it will, and potentially with wall thickness. So let me turn that off, and I'll just show the wall thickness first. So threshold of 2. Now what I'm going to look at are these bottom bits, these discs particularly. So if I click on them, I can see they're all 1.5. That's how thick they are. That's a bit thicker there. That bit there is 2.75 because it goes on to, it's joined up with that part there at the bottom. But generally speaking, they're about 1.5. So how wide could we make those discs? Let me turn that off and calculate protrusion. So I'm going to isolate those by looking at regions below a thickness of 1.6 and then calculating the protrusion mesh. Now this takes a little bit of time. One thing I should point out is when I'm clicking these buttons, I'm actually calculating both the wall thickness mesh, or in this case the protrusion mesh, and the gap thickness. That's just how I've implemented it in this demo. You don't have to do that. I did it that way because it seemed like it would be nice to switch between them quickly, but of course it does mean that it takes longer to generate the initial meshes. Okay, so that's done that. And we've got a thickness of 2 here. So if we zoom in and have a look, what that's telling us is that all these green and red regions are thinner than a 1.6 thickness. But going out along this disk, this green region is within 2 of the grey, which is a valid thick region. So that's within 2, and then the red region is beyond 2. So if we click on this surface, for example, that's 0 because it's in the thick region. Then we've got 0.3, 0.7, 1.7, 2.2. And if we go out all the way, then we're at 7.5. So again, if I change this to say 5, and we can see the green regions have expanded and the red regions have contracted. So let's say that for this size of thing with your material on your printer, 5 was as far as you could go, then you'd immediately know, well, hang on a minute, I've got a problem here. These discs look too wide for me to print. But also it's also picking up the fact, so on the base here, so these things are fine, they're thick, there isn't a problem, but these 2 on the end are a problem. They're below the 1.6 region, and here I've got 3, 2. When I get here, I'm above my 5, so yeah, I can't print that. And similarly, this little end of that thing there, so that's just too far away from that thick bit to be considered suitable for printing based on these tolerances. So that's the general idea behind the protrusion mesh, and I'm just going to show you one more example. So here's a sort of topology optimized saddle, and I'm going to look for let me create a, I've forgotten the magic numbers, so let me actually create the wall thickness first. And I'm interested in looking at these narrow struts. So let's just see how thick. 2.2. Okay, so let's create a protrusion mesh of say 3, and click on wall thickness to create it. And so there we go. What we've got here, I mean, it's computed 2.3. So these struts are mostly thicker, although you can see there are some thin regions. There's some thin regions that are green. I mean, 3, less than 3 with a thickness of 2.3 seems a bit harsh. So let's go to say 4 and see, or even 5 seems safe to go to. So here we've got regions that are thinner than 3, and we're looking for, we're colouring in red anything that's more than 5 from an anchor point that is a thick region that's more than 3. So you can see along this strut, here I've got 1.5 because we're measuring against this region, and 3, and then here it gets above that. Now, obviously, if you were printing this, it would actually, you wouldn't have those anchor points in place at some point in the printing process. So you'd need to sort of you might be orienting it when it's printed. It might be in that orientation, for example, and you might want to print up. You would be printing up from this point of view, from the bottom upwards. So if you wanted to do that, you could simulate that using Polygonica by taking slices, extruding each slice, and then booleaning it to the previous slice, and then doing a protrusion mesh analysis as the thing's being printed, as the thing is being printed. And that would give you an actual simulation of the printing process, and you'd see if anything was getting too long. It would take a while. We'll probably do a demo of that in a future video as well. But it just shows that the values here are not based on the orientation within the printing process. So that one's 0. If I double click on that one, I'm in the green, which is 2.5, and here I'm in the red, which is 8. The other nice thing here is it's not just picked up the potential issues with these thin struts. It's telling us also that, this topology optimized thing here, well, we actually might have a problem in that region, and in that region as well. So it's quite nice for picking up these potential problems. If I make this number a bit bigger. Oh, no, possibly I was expecting to see a problem on the saddle tip there, but I guess 3 I guess it's thicker than 3, so it's not a problem. If I recreated this with 4, then I would see a problem there. Of course, I've done something I always do. I've done this the wrong way. So in fact, yeah, if I look at this, I'm decreasing the allowable threshold distance from a thick region, and then we do see that there are problems in this area if you have if you have a very, very short distance. So the distance from this red area to the thicker grey areas here is 3.9, so it's not very far. It's not really a problem, but I just show that as we decrease rather than increase that, then we get more red regions. My bad. So that's the end of this demo. Thanks very much for your time and for listening. If you want to get in touch, you can contact us via the website, the contact page on the website at the top there. Or you're very welcome to connect with me, Richard Baxter at MachineWorks, on LinkedIn, and send me a personal message. And I'll be happy to answer your questions about Polygonica. So thank you for your time.